Hello everyone, good evening. I'll be starting in another 1 or 2 minutes. Hello? Hello? Uh, am I audible? Thanks, Sarah. Yeah. Welcome to week 7 of Fundamentals of Micro and Nanofabrication. Thank you so much for joining for this tutorial session. So, in today's session, we will be talking about optical lithography. Let's go ahead and do some problems in optical lithography. Okay, the first problem is, this is a previous year quiz problem. So let me read it. A lithography exposure system uses a wavelength source of 436 nanometer. When the light passes through a mask with a uniform line and space structure, a second diffraction order with an angle of 45 degree is formed. So yeah, it's a optical litho setup. We are illuminating a mask with a desired wavelength of light, and then through this mask the light will pass, and then it will diffract, and then it will go on to a substrate with photoresist coating on it. So that is the general setup. Now they have told us that the second order diffraction has an angle of 45 degree. So this is for the second order diffraction, and so what they want us to find is determine the pitch of the line space structure on the mask. Okay, so the mask is a periodic multi-slit interferometer like arrangement, and the pitch is given to be P. So the pitch is the distance between the different transparent windows of the mask. So what we have to find this pitch P. So the way to do it is we basically need to find the relation between the pitch P and wavelength lambda and the angle of diffraction for different order of modes. So the way to do it would be simple, like just like in a like we can consider a two slit experiment for now. Like we had studied in our previous classes, for a two slit Young's double slit like experiment, when light passes through this coherent light, so we have light from a single source lambda, and it's passing through both the slits, there will be interference that will be happening from both the slits. So here we will see a such pattern, right? So this is the central maxima, and then there will be other first order, second order maxima, corresponding maxima. So this +2 is nothing but second order maxima. So for the second order maxima to happen, the light from both these slits should interfere constructively here, right. So, for constructive interference, what should be the path difference? The path difference has to be a multiple of the wavelength. So, from our optics courses we know that the path difference for constructive interference is some n times lambda. So, in this case our n is 2. So, this is the 0th order, this is first order, this is second order. So, this n will be nothing but 2. So, basically what this means is the path difference for the central maxima will be 0. For the first maxima it will be 1 lambda, and for the second maxima it will be 2 lambda. Okay. So, now this is what the path difference is supposed to be, that is 2 lambda. But geometrically what is the path difference? So, this distance is pitch p, right? This is p, and assuming that the wafer is quite far. So, this is the mask, this is the wafer. Assuming that this is considerably far compared to this pitch p, we can say that this distance is approximately the same as this distance. So, the distance from A to B is approximately same as B to C. So, the path difference is arising only from this path CD, from this portion CD. So, what is that that we have to determine? So, this CD is nothing but so another thing that is given to us is that this angle is 45 degree. Okay, so this is making 45 degree with the optical axis. So, this angle is 45 degree, that means so this is 90. I will just draw this again here. So, this is 45 degree. I have dropped this as at 90 degree to the next ray from the other slit. So, this is 90 total. So, this will be 90 minus 45. So, this is again 45, and this is the mask, right. So, this will also be 45 degree. So, this is 45, this is P, that means this will be what? This is 90 degree. This will be nothing but P sin theta, right, P sin 45 degree. So, P sin theta is equal to 2 lambda. So, from this we can simply get P to be 2 lambda by sin 45 degree. That is nothing but 2 into wavelength they have given, right, yeah, it is 436 nanometer upon sin 45 is 1 by root 2. Upon solving this, you will get pitch to be somewhere around 1.23 micrometers. Yeah, so this is okay, right? So, only thing to remember here is pitch P sin theta is equal to n lambda. So, n is the diffraction order and theta is the angle for like the diffraction angle of that order. So, the angle with which the diffraction angle of the diffraction order. Okay. So, yeah, so let us move on to the second part of the problem. So, in 1b the problem state like background is the same, only thing is that now they want us to calculate diffraction angle theta 1. So, the angle corresponding to the diffraction order of plus 1. So, how do we calculate that? Again we can use the same formula, P sin theta for theta equal to plus 1. So, I will write it as theta 1 is equal to n is 1 lambda. So, sin theta 1 is equal to lambda upon P. So, this is straightforward. We just put the value of lambda. Lambda was 436 nanometer upon P is we just determined in the last question, P is 1.23 micrometers. Yeah. So, on solving so theta 1 is nothing but sine inverse of this. And what else have they asked us? For the first diffraction order, estimate the numerical aperture. Numerical aperture required to capture the first diffraction order. Okay, so what is numerical aperture? So this is a projection lithography setup. So in projection litho, what happens is, so we have some source which is giving us the light of the desired wavelength. Then we have we are having a mask. So there will be some projection optics before this also, but essentially we have a mask, and between the mask and the wafer there will be a lens. So it is not just a simple convex lens, it is a huge lens setup. However, the only thing to understand here is, so whenever a source is incident on a mask, what happens is there will be diffraction that is formed. So various diffraction orders will scatter or will be formed, and as they propagate, the diffraction angle will make sure that they propagate outwards. So now this lens, what the purpose of this lens is to capture as many diffraction orders as possible and focus them on the substrate. So based on how well we can focus on our wafer, that will decide the resolution that we get on the wafer. So so the numerical aperture of this lens is very important. Now and the numerical aperture will actually determine how many orders or how many diffraction orders we can capture and project it on the wafer. So they have asked us the numerical aperture required to capture the first diffraction order. So that means that we need to capture theta 1. So the formula also they have given us. So the numerical aperture required to capture theta 1 will be nothing but n sin theta 1, and we are assuming that there is it is not an immersion litho setup, it is just air here. So n equal to 1 here, so that will be nothing but just sin theta. So that is nothing but 436 divided by 1.23, and yeah, if you do it, it will come out something around 0.35. Yeah. So this was also a quiz problem that came that was asked in previous year. Okay. Again a simple formula based question. Considering a depth of focus of 194 nanometer, so they have given us the depth of focus. Estimate the resolution. Yeah, estimate the resolution within the theoretical limit. So the formula for resolution, the theoretical resolution of any optical lithography setup is basically resolution, the minimum width that we can resolve is given by lambda upon Ne. So this is a general formula. In general, this is not true, it is more like proportional to lambda by Na, but theoretically we should be able to get resolution of lambda by Na. Okay. So we have to find the resolution. They have given us the wavelength lambda directly, but they have not given us the numerical aperture. So we need to find out the numerical aperture. So like I said in the previous problem, the larger the numerical aperture, the smaller will be the I should not write resolution here, this width that we can resolve. So the smaller widths we can resolve. So that will mean that the resolution is very high. So let me just correct it. Okay, so so theoretical resolution is lambda by Na. So yeah, so we desire larger numerical aperture so that we can gain, get information from multiple diffraction orders and then project it on the wafer. Yeah, but then how do we find out this numerical aperture? So the numerical aperture is actually related to the depth of focus. So what is depth of focus? Depth of focus is basically the distance between the two planes. So say I have a projection system, any optical projection system, it can be a microscope or a lithography system, any system, um, uh, the there will be, like when we are projecting onto some surface, there will be tolerance limit within which the projection we can do reliably. So, um, the focus is reliable for the two planes for which the focus is reliable, the distance between these two planes is the depth of focus. So, like for the distance from the lens, how to say, for the distance from the lens in between these two planes, the focus will be reliable. We would be able to project and write on our wafer reliably when the distance from the projection optics is lies between these two planes. So, this is nothing but the depth of focus. So, this depth of focus is actually related to the numerical aperture. So, the formula is given by depth of focus is equal to it's related to wavelength as well, lambda by 2 Na square. So, how this formula comes is it's a bit complicated, but we just need to remember the formula. So, depth of focus is nothing but lambda by 2 Na square. So, from this we can get the numerical aperture easily. So, numerical aperture is nothing but lambda over 2 times depth of focus square root of this. So, it is just a matter of formula substitution now, and we can get 365 upon 2 194 yeah 1 by 2, and that will come out to be somewhere around 0.97. So, if this is 0.97, then what will be my resolution? The resolution will be, so resolution is minimum width that I can write or that I can resolve. That will be nothing but 365 divided by nanometer divided by 0.97. That will be some 376. Like, if you see, it's very close to the lambda wavelength. So, yeah. So that's why we usually say, like, reducing the wavelength gives the best effect at increasing the resolution. Okay. So yeah. So yeah, this was also a quiz problem. Another quiz problem. From the schematic shown below, which of the following depicts the overexposure of negative photoresist at a constant development time? Okay. So in this we need to understand what is a negative photoresist. So there are two types of photoresists. I have discussed this before also, so I will just tell quickly. So positive photoresist, hello. Okay, hello. I thought I heard some. Okay, yeah, positive photoresist. Positive PR is one where the exposed region will be removed post development. So yeah, so in this case, like we are exposing the photoresist through some mask, whatever is exposed that will be removed after you develop. So yeah, so it's the opposite in case of negative photoresist. In negative photoresist, exposed region will not be removed, and rest everything will be removed. So only that portion will be will stay there, it will get hardened, and rest of it will be dissolved in the developer and will go away. So yeah, one thing to understand is it won't be removed just by exposure. We have to also develop after that. So these images are after the development. So A, B, C, and D. So based on these definitions of positive and negative resist, what do you think is an overexposure? Overexposure means we are exposing for a longer period of time, or the dose is very high. So which of these do you think is a overexposure on a negative photoresist?
Third option.
Third option. Okay. So Yeah, it is clearly a negative resist because only the material is preserved in the region where the exposure is there. But why do you say it is overexposure?
because the size width of the T of photoresist is less.
Okay, so the chemistry is such that whatever part will be exposed will stay there. So if I expose for longer time or with a higher dose, um do you think that it will become more hard or it will dissolve easily? It should become more hard, right? Overexposure
Yes,
means I am exposing it for longer duration. So, so it should have become more hard. Why did these parts disappear if it was overexposure? Uh, that's why the correct answer is D actually. So, do you understand my reasoning? So, after overexposure, what will happen? The chain reaction will be such that it will even expose the adjacent regions. Or rather it will even harden the adjacent regions. So, the exposure will be so the material that gets hardened will be more than what is required. Uh,
yes, ma'am.
okay, it makes sense, right, Raj?
Yes, yes,
Okay,
totally.
thanks. Yeah. So, okay, so the next problem is interesting. So, now we have to write this pattern on a wafer. So, pattern to be written, the top view I am showing. So, imagine this is a wafer. For some reason I drew it as square, but it's just a wafer. The white region is a silicon wafer. So, the stack is like this. It's a silicon wafer and I want to pattern. So, there is an oxide region above this silicon. From this I want to pattern it such that I get a silicon wafer with such design of oxide on top. So, there should be a square patch of silicon dioxide and there should be a hole inside it. So, this part is removed. Sorry. So, how do you think we can do this? We have two masks for doing it. We don't have a single mask with the exact design. Instead, we have two masks. Mask 1 is like this and mask 2 is like this. So, now we have to devise a possible process flow for getting this type of design on my wafer. A square, and within the square I need a circle. So, first of all let me explain what this color scheme means in this mask. So, wherever it is orange, that part is opaque, and wherever it is white, that part is transparent. So, light will pass through these regions and light will be blocked in the orange region. Similarly here also. So, these two masks are available with me and with these two I need to make this pattern. So, can you tell me the process flow? Okay, I'll help you out. I'll start. Uh, so, first thing is pretty obvious. We'll first coat photoresist. Coat photoresist. So, again I have silicon, I have oxide, and on top I will coat photoresist, PR. Now, I need to pattern this resist, right? So, I will need to expose it with one of these masks. Say I first do the square mask. So, for patterning with the square mask, do you think I should use a negative photoresist or a positive photoresist? So, this photoresist should be what? Positive one or negative one? So, the mask cross section, if you look at it, it will look something like this. So, it is blocked on the side, center it will be open, next side also it is blocked. So, the light will come in the square region and this is the PR. Okay, so should I use a negative photoresist or positive photoresist? Okay, Mir is saying negative. So yeah, you are right. Since the exposed region needs to survive, so the oxide in the exposed region needs to survive, and the rest of the oxide we need to remove. So we will use a negative PR. Okay, so I used a negative PR. So all these regions were exposed. Okay, so the next process will be, so next process will obviously be development. So after development, my sample will look something like silicon, SiO2, and I will have PR only in the exposed region. So after development, what will we do? After development, we need to etch it, right? So I'll in, because there's not much space left, I'll just write it here itself. Development plus etch. Uh, so then after etching, the regions which are protected by the PR will remain, and rest of the SiO2 will will be etched away. So after etching, I will get something like this: silicon, SiO2, and then PR on top of it. So how do we etch it? We can use some dry etch technique, like so silicon dioxide is mostly we can etch it with a dry etch fluorine chemistry, reactive ion etching. So we can use something like that, RIF. So about the etching techniques we will learn in next classes, but for now just know that we can do it. We can etch away SiO2 when we are protecting the part that we require with a photoresist. Okay. So now I need to remove the PR. So for this we have studied how we can remove photoresist, right? So we can do, we can maybe do like different cleaning methods are there, right? They work even for the photoresist. So we can do an acetone IPA clean, and then after followed by a piranha clean. Or there are special PR removers also available that we can use them to get rid of this photoresist layer. So then finally we will just have silicon and SiO2. Okay, so far so good. Now we want to etch a hole through it. So how do we do that? So now the mask will look like, so there is just an opening for the hole. So the mask will look like this. It's opaque here, some hole it is open, and then again it's opaque here. So now which resist should I coat this material with? So should I coat my device with? So now I want to etch through this hole. So whatever is exposed, I want to remove PR from there. So if I want to remove PR, I'll use a positive resist. Correct. Yeah. So I'll use a positive PR. So then again the same process will happen, and we will be able to etch away this. So for the final device will look like silicon, SiO2 and SiO2. So I am able to get a device like this. Okay, so we were able to do this. So in the like a similar problem, now what we have what they have asked is, okay, so now the mask writer, okay, I'll tell one thing. So in this case we assume that we have these two masks, right? So but we need to write these masks also. So um, so it's like when we say we are doing lithography, we are transferring the design from the mask to our wafer or to our substrate. But how do we write the mask? So for writing masks, we have something called as direct writing. So it's like a laser pointer or a electron beam electron gun. The laser beam or the electron beam will directly write on the substrate. It will like without any mask layer in the middle, it will directly trace the line that I want to write. So that is what a direct writer does. But so for writing masks we use this direct writer, but the resolution of a direct writer is limited to 5 microns. Okay, so it can only write 5 micron features reliably, but cannot pattern features smaller than 5 microns. But now I want to write a line of width 2 microns. So what are the possible ways that I can do this? Okay, so yeah, so I can only make masks with 5 micron lines or more. So it cannot go lesser than 5 micron. But my wafer, so this is just a mask. So on my wafer, I want the line width to be 2 microns. So can you tell me some ways in which we can do this? Anyone wants to take a guess? Like a lot of methods were suggested in class, I think. Um, So one thing is why we are limited to this 5 micron resolution. You can say that if I go to lower wavelengths, so if the direct writer uses a layer which has direct writer uses a laser which has wavelength which has lower wavelengths, then we can write even smaller features, right? So we can reduce lambda. Go for lower lambdas. Yeah, so why am I saying this? So if you remember, in case of proximity litho, if you remember, there were three types of contact lithography, proximity. So these both are Fresnel diffraction limited, proximity and projection. So we usually don't use contact lithography because of all the contamination issues and the mask lifetimes also. So mask lifetime will be very low for contact litho. So we usually go for proximity and projection. In both these cases, the resolution is dependent on the wavelength lambda. So for proximity litho, we will have the smallest width that we can write, or the resolution is root lambda by g for proximity. For on the other hand, for projection, we will have this as just now we discussed lambda over Na. So in both these cases, it is depending on the wavelength lambda. So if we go for lower lambdas, we can probably write smaller than 5 microns. But say that this direct writer we are saying that this is existing setup and we don't want to change anything. We cannot change anything basically. Then what do we do? So another option is to increase the refractive index. So if you remember, in like just now we discussed, in proximity there will be mask, and below the mask we will keep our substrate on which we want to write something. Okay, so maybe some layer and some stack. So in between these two things, if we put some material of higher refractive index, say earlier it was n equal to 1, now I have something like water or oil, n oil is greater than n air. So it is higher refractive index. Then what will happen is the resolution, so the wavelength, effective wavelength will become lambda over n. So earlier n air is 1, so it is lambda, but when we put something like oil, it will become n oil. So n oil is greater than n air, means lambda by n will reduce. So the effect will be similar to going to lower wavelengths. So this is called as immersion litho. Similar principle will also work in case of projection litho. So yeah, so this technique is also there, in which we put some higher refractive index material in between the mask and mask and the substrate, and that we can by using that we can effectively reduce the wavelength and again get a finer resolution. But say we cannot even do that. There is still a much more elegant way to get a 2 micrometer line width. So, I am saying that we just need a 2 micrometer line. We are not saying that we need multiple such lines or anything, just a single 2 micron line. So, it is possible, and how we can do it is by using like just we discussed in the previous question, right, overlay. So, we can have two different masks and pattern them on top of each other in such a way that the width of the final line that I get is 2 microns. So, I will just write it down, that it will make it clear. So, say I have these two masks. So, my mask 1 is and this is 5 microns, and my mask 2 is so when I write them on like one after the other, just like we did in the previous case, what I intend to achieve is so this is my 2 micron line. The exact process flow we can discuss, however it is the same like we did before. Okay, just for the complete like sake of understanding, we can do it once. So, okay, I will just take another slide. Okay. So, say again like in previous case I have some stack silicon, say again oxide only, SiO2. Now, I want to write a single line in this oxide layer. So, first I will expose it with a mask of 5 micrometer width. So, which resist should I coat it with? Negative resist, right? Because I want to keep this region and remove the rest of the region. So, this is negative. So, then after developing plus etching plus PR removal, I will get, just like we discussed in the previous question, I will get the silicon dioxide here, and the PR we removed by acetonoipiacline or pyranacline, and now we have this. Now, we will coat a next layer of PR on top of it. So, yeah, it might not be very uniform because of SiO2, but it still works as I just need to etch this portion, I do not need really care about the rest. So, again this time I will use a mask which is say I want to keep this much region, I want to remove from here. So, I will use a mask here like this and here. So, this is again 5 microns or more, but now the resulting dimensions will be, so this is called a so I have got a 2 micron strip. So, this is called as double patterning. It is a very powerful technique. However, it will not work very well if like you can imagine many scenarios in which, like if you want to make these lines very close to each other, then you can't, because in one go you will etch at least 5 micron width. So, yeah, so you can't have many multiple lines close to each other. Also, it won't work if you want to do a shallow etch. Now, in this case we etched all the way till silicon, right. However, if I wanted to, like if I had only silicon here and after etching I wanted a profile like this in silicon itself, then with the successive processes the other portions will also keep on etching. So, in this case, because I went from silicon dioxide to silicon, the etch recipe was such that it will not etch silicon. So, it was a um, what to say, so it will stop the etching process there. However, if I uh, needed to do shallow etches, then this would not have worked. So then I would have got a profile of SiO2 instead of a flat line here. So all those things are there. So it doesn't work all the time. However, it's still a very powerful technique for going to lower dimensions when we have small lines far from each other, and yeah, and full etch lines. Okay. Okay. Now this is a very easy question. Um, the resolution in optical lithography scales with the wavelength of the light source and numerical aperture. Yeah, just like we discussed before, resolution. So the width that I can resolve is directly proportional to lambda over Na. Assuming k equal to, yeah, so the proportionality constant they have given, k times lambda over Na. K equal to 0.4 and numerical aperture values of so and so. For a standard lithographic wavelength of so many, what are the combinations of Na and wavelengths that can be used to print 200 nanometer features? Can you guys try and let me know? So we have already discussed this formula, so it's just formula substitution. So which all numerical apertures and wavelengths we can use to get a print of 200 nanometer features? So uh, basically we need to find out the W. So they have given us that W has to be 200 or less, like, so that's what we mean by so the resolution has to be greater, like small, like the width that we can resolve should be smaller than this, only then we can print 200 nanometer features using this uh, uh, these combinations of aperture and wavelength, or this recipe. So yeah, so we just need to do this. Point 0.4 times 248 nanometer on 0.5. So you can try doing this. So this will come around somewhere around 190 something, I think. Uh, yeah, 197, 198, I don't know, but yeah, you can try it for all the combinations, and it's just the formula substitution. So uh, so whichever W comes below 200, those options are viable, rest are not. So I think one is viable. Two, yeah, you can do it. It's like it's just formula substitution. A lithography engineer diluted a photoresist solution with a thinner into 4 different ratios, PR1, 2, 3 and 4. The graph shows the relation of the photoresist thickness with the spin speed of the 4 different PR solutions. Based on the plot, identify the photoresist with the highest viscosity. Okay, so when we coat photoresist on a substrate, we usually use the technique of spin coating. And this spin coating is done by placing the wafer on a chuck, and then we rotate the chuck so that the wafer also rotates, and based on the viscosity and everything of the photoresist, sometimes we require to thin the photoresist. So what happens sometimes is when we are spin coating on the wafer, there will be some, like it will deposit all over, and then there will be some bead, edge bead, so it can be reduced by thinning. Also sometimes for getting higher resolution we need very thin films, so for getting the desired thickness of films also we do this thinning. And also the thickness of the film will also determine the dosage that you will require while doing the optical lithography. So for all these things we quite frequently use thinners, and so yeah, so these thinners will decide the thickness of the photoresist. So photoresist coating. So based on these graphs, if you see PR1 has very high like higher resist thickness compared to PR2, 3, 4. So yeah, so one thing we notice is with increase in spin speed, obviously the resist thickness will reduce, because it's just a viscous fluid lying on top of a spinning wheel. It will fly off, right? So higher the viscosity, uh, more difficult it is to fly off. So that means that PR1 has high viscosity, so that's why it is staying. Uh, it is having a thicker coating compared to PR4. So what did they ask? Identify the photoresist with highest viscosity. Yeah, so PR1 has highest viscosity. Yeah, PR4 has minimum viscosity and these two have intermediate. So highest viscosity means it was not thinned much. Other solutions were thinned in some solvent or something. Okay. Yeah. So this might happen that you are doing a contact lithography, but your wafer is not uniform. So the wafer is slightly bent, and the bent profile is shown in this figure. So like edges have gone down. Okay, so yeah, so between point A and B you see that there is a 10 micron difference. So they are telling that a wafer bow introduces a height difference of 10 micrometer between position A and position B, as shown in figure A. If the wafer is exposed using contact optical lithography, so they are told that they are using contact litho. So at the center at least there is a perfect contact through a mask that has a uniform opening of 1 micron. So the mask has periodic 1 micron openings. Assuming a diffraction angle of 10 degrees, so they have already told us the diffraction angle. Estimate the change in dimension at position B. Yeah. So now there is a 1 micron opening. Okay. And 1 micron opening, when we are since it's not a contact litho anymore, there will be some gap. So say this is the wafer, or this is the PR on top of the wafer. Then this 1 micron won't just come and sit and write directly here, right? There will be some diffraction, and because of which it will spread. And they have already given us the angle of the spread. They have told that the spread angle is nothing but 10 degrees. So from this, estimate the change in dimension at position B. It's a trivial problem, but sometimes, like seeing the question for the first time, someone can get confused. So yeah, so it's just a geometrical problem now. So they have given us that this is 10 microns, this is 10 degree. So we have to find out how much is this. So say this is x. So x is nothing but x over 10 is tan of 10 degrees. So x is tan 10 degrees times 10 micrometer. So this comes out to be 176 nanometers. And then this is not just this 176, right? They are asking us the change in dimension at position B. So change is nothing but x plus x. So that is 2x. 2x will come out somewhere around, I don't remember the answer, some 300 something. Okay, that's not the point. But the point is that we should remember to do this 2x. Yeah. The profile of a positive photoresist at different exposure doses is shown in figure. Yeah, similar problem we did last time also, right? What are the critical modulation transfer functions and the resist contrast? So, yeah. So, what is first of all modulation transfer function? Modulation transfer function is nothing but the image contrast that we see for a projection based, or for a, even for a normal what is it called, proximity based litho system. So whenever there is a slit or multiple slits, there will be diffraction, and these diffractions will interfere with each other and they will form an aerial image. So at some positions they will have a maxima, some positions minima, like that. So if there is a screen here, it would have formed a series of maxima and minima. So this is the aerial image. So the contrast of this aerial image is given by this modulation transfer function. So it is nothing but I max minus I min upon I max plus I min. So this contrast has to be high enough for the photoresist to realize the contrast. So the minimum contrast that is required for the resist to change from its hard state to its easy to dissolve in developer state uh, is the critical modulation transfer contrast. So the critical modulation transfer contrast can be we can get it from the resist versus dose curve. So the minimum intensity contrast that we require will be nothing but the contrast of these two energies, right. So that is the full exposure energy and this is the minimum exposure energy. So that will be critical modulation transfer function contrast is nothing but 90 minus 40 upon 90 plus 40 millijoules per centimeter square. Yeah, that will come out to be somewhere around, that is only 50 upon 130, that is somewhere around 0.38. So that is that. And resist contrast, like just like we did in the previous class, resist contrast, I will just write the formula, nothing by 1 by log of E2 by E1. So you can find out the resist contrast. Problem 10. So this is anti-reflection coating is used to reduce standing waves in a photoresist. If the thickness of anti-reflection coating is so much for I line source, assuming the refractive index of photoresist remains unchanged, what will be the required ARC thickness for G line source? That's fine. Yeah. Okay. So first of all, why do we need anti-reflection coatings? So what can happen is, in a photoresist, so this is silicon, say this is my PR, when I am illuminating this, sometimes what happens is there will be reflection from the surface. So there will be reflection from most of the surfaces because of the refractive index change. However, what will happen is there will be a back reflection also, and then it will keep on happening. So it will form like a cavity here, and because of that we will see some ripples in the so PR will develop in regions where we don't want it to develop, and it will harden in regions where we don't want it to harden. So there will be some like sometimes on the edges we will see some standing wave like patterns. So if this is my PR, the development won't be smooth, we will see some roughness on the edges, or sometimes the what did I want to say? Yeah, so there are certain other errors also, like if the PR is not uniform, so in some places the PR was thicker, some places the PR was thinner, then in those places say it completely dissolves from this region, however from this region it does not dissolve, some part is left, like So the non-uniformity in PR won't be tolerated much because of this effect. Uh, yeah. So usually what we expect is for small variations of PR, if this reflection was not there, it would have not affected the development time and dose requirements as much. However, because of these things, these non-linearities in the process, the slight changes in PR thickness or dosage will change the patterns that we see on the device drastically. So for that, it is essential that we reduce the uh, this total internal reflection, or this cavity, the light getting trapped in the cavity here, and for that they use something called as an anti-reflection coating. So it is basically a medium which has very small optical contrast or refractive index contrast with the PR. So the light won't reflect from here, it will pass through and go to this interface, and this thickness of this anti-reflection coating is chosen such that when the light comes back and hits here, these two things are out of phase with each other. So when they are out of phase, there will be destructive interference, and so uh, there won't be any mode that is trapped inside the photoresist. So there won't be any constructive interference, and that's why there won't be any light that is trapped inside the photoresist. So that is the purpose of anti-reflection coating. Uh, yeah, so now the question is asking that if the thickness of ARC is 73 nanometers for I line source, so for 365 nanometers, the thickness is 73 nanometers for ARC thickness. As a rule of thumb, ARC thickness should always be lambda by 4, or since the ARC has some refractive index, it will be lambda by 4n. So only then the path difference will be equal to lambda by 2, and when the path difference is lambda by 2, we get a, so since it is travelling twice, it will be lambda by 2. So if path difference is lambda by 2, we will get destructive interference. So for destructive interference, the ARC thickness should be lambda by 4, and since the refractive index is n, so lambda by 4n. So n is refractive index of ARC. Sorry. Okay. So for 365 nanometer source, the ARC thickness is given to be 73 nanometers. So then for G line source, G line is 436 nanometer. What will be the thickness? So it's just 436 upon 365 into 73. It's directly related, right? Directly proportional. So yeah, whatever you get is the thickness. So only thing to remember here is it is directly related to lambda, and yeah, this something in 80s you will get 84, 85, I don't know. In proximity litho, what should be the gap to obtain resolution of 1 micron using eye line of mercury arc source? Okay, so they have given us the resolution. So W is 1 micron, 1 micrometer. Uh, yeah, W is nothing but root of lambda g. So g is the gap. So just by using this formula, we can get what should be the gap? G should be W square by lambda whole root, right? Yes, this they have given to be 1 micron, lambda is given to be 365 nanometers. So from this we can get gap. Yeah. So again just formula substitution. Yeah. So that's it for today. So most of the questions today were just formula substitutions. However, I hope I did some understanding based questions as well. Okay, so any questions?
Do you have these questions, whatever you have solved? Can you share with us with solutions? Is there
I can
anything
share
available?
the PPT with you. So
Okay,
these questions, like these are I took just from the quizzes, previous time quiz. I can share the link, but I don't think it will be accessible to you. Uh,
okay.
and these ones I just prepared it myself. So I think the PPT is the only thing that I have.
You don't have it with the solutions.
No,
Okay, okay,
I mean. So some of them I have, but the link is not accessible to you. So they gave me a special login access to the previous semester course, like
okay,
previous
okay,
run of the course. I don't think you can
okay.
open it.
All
Yeah,
right, noted.
yeah. Probably for the next assignment, I will do some questions which I got in like my like when I did the course. So those assignments I would have written solutions for.
Okay, okay.
Okay. Yeah. So, do you have any questions from the previous quizzes that you might want me to discuss? So, I'll just note them down and do them in the next class or something. Not this.
I think so. Assignment four, five, or six has some questions. I'll just check and I'll mail you.
Sure, that will be great. Yeah.
Yeah.
Okay, then. Thank you.